This is the Chem 1 lecture over properties of acids and bases. And just so you know up front, this lecture is over 2 days. And so every class period ends possibly in a different place. This will be one lecture, but just know if you're in class, this was over a 2-day period. So if you've only missed one of the days, either speed through to what's new or, just do your best with it. Okay, so let's start off actually with a review. Back in Unit 8, we taught you guys how to name acidic compounds. And so they were anything that started with an H. And so we said what's really attached to the H is how the naming system works. And so if it's just hydrogen attached to one other element, like chloride or bromide, then you're going to use the phrase hydroic acid. So for example, HCl would be named hydrochloric acid. Typically, this system works for hydrogen attached to something from the front of the periodic table. If you have something attached to hydrogen and that group name ends in "ite," like if you had sulfite, H2SO3, we swapped out "ite" for "us" acid. So this was sulfurous acid. And then if the group attached to the hydrogen ended in "ate," you swapped out "ate" for "ic" acid. So if you had HNO3, that polyatomic is called nitrate. It swaps out for nitric acid. So let me write a few practice problems. HF, HClO2, H2CO3. So considering that we're starting a unit all about acids and bases, you're definitely going to be seeing a lot of acids, whether in formula or name, so it's good to remember how we name them. So HF would be hydrofluoric acid. HClO2, that group is called chloride, that polyatomic. So ite goes to us, that would be chlorous acid. And then the next one, that's carbonate, so this becomes carbonic acid. And let me just throw this one in there, HC2H3O2. It always looks intimidating because there's so many elements going on, but that group is called acetate, and so also known as acetic acid. Common name is vinegar. Vinegar. Not sure. Something that we didn't necessarily call it a base, but in our nomenclature unit, you did learn how to name this because it fell under ionic. Later in here, you'll learn bases typically end with hydroxide, with OH. So Mg, OH, Fe, OH3. So this would have just been under normal ionic compounds, and if you remember ionic, you name the metal, check to see if they need Roman numerals, and then you name the non-metal. And so this first base would be sodium, and does not need Roman numerals. And then OH is a group, a polyatomic called hydroxide on the back of your periodic table. MgOH2 is magnesium hydroxide. And then this next one would be iron. This is an unpredictable charge, so it's going to need Roman numerals. Hydroxide. And if you remember how to do Roman numerals, you work backwards. We know that hydroxide's -1, but there's 3 of them, so that's an overall -3. This iron must be carrying a +3 charge. And then like Unit 8, also be able to work it backwards, where we give you a name and you write a formula. So if we give you hydrosulfuric acid, we know acids have a hydrogen ion. Hydro indicates only one other element, which would be sulfur, which is a -2. So for this to be balanced, we need 2 hydrogens and a sulfur. For a base, it could be something like zinc hydroxide. Zinc was a part of that special staircase we sometimes called Katzenagel, but even though it looks like it's in the unpredictable charge, it always carried a +2 charge. Silver was +1, aluminum was +3. Hydroxide carries a -1. So in order to be balanced, you would need 2 hydroxides to balance that +2. And so parentheses, 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 that was what was most missed in Unit 8. So flashback to Unit 8, nomenclature does appear in this unit, but specifically about acids and bases. Okay, we're first going to focus on acids, and then we'll focus on bases. And so you can just highlight these in your notes, but we do want you guys to know properties that are distinguishable for acids. And one is that acids typically have a tart or sour taste. So you can see, picture like lemons. There's citric acid in there, and lemons have that sour taste. Acids, when dissolved in water, they're going to break up into ions, and so based on that, they can conduct electricity, and so they're called electrolytes, but acids conduct electricity when in solutions. Another property to know about acids is how they behave with an indicator. So by definition, an indicator, it's indicating if something is an acid or a base, and you'll see that by a color change. There are many, many different types of indicators. One of them that you'll eventually see in lab is called litmus paper. It's a piece of paper, and if you dip it into something that's acidic, the paper is going to turn red. And if the paper was red, it would stay red. Another type of indicator that you've actually already experienced in lab, like last semester, was phenolphthalein. And so you would drop a few drops in, and if it's acidic, the solution would stay clear. And then we're jumping ahead, but if it was basic, it would turn that pink color. There are a few natural indicators. One of them is cabbage juice. So if you kind of boil this down and get cabbage juice, the cabbage juice will change colors based on if it's acidic or basic. Hydrangeas will turn different colors based on the pH of the soil. And so that's kind of cool. If it's like basic, I think it's more purple, and if it's acidic, it has more of a pink color to it. Acids can be classified as strong or weak, and I would just say be careful with this term, because I think we like to think that strong, we really are saying something's concentrated, like it's 12 molar, and weak is it's not. That's not what strong and weak mean, okay? Strong and weak has to do with how something behaves in water. So a strong acid is going to completely break up, ionize, dissociate, all mean that same thing. Versus weak acids are going to only partially ionize. So let's first just talk a little more about the word dissociate or ionize. So when a hydrogen ion breaks apart from the acid, dissociates, what happens to it? The hydrogen gets absorbed by water, making a hydronium ion. So for example, when hydrobromic acid is placed in water, this hydrogen is going to break off. It's going to ionize, but then it's going to get absorbed by the H2O. So then your resulting things would be a hydronium ion and a bromine ion. This is making the solution acidic. Okay, this next part is a little bit awkward in your notes. They want you to draw an arrow. So for a strong acid, H with the theoretical A, when it's placed in water, they want you to draw a one-way arrow. So that acid is going to completely ionize, 100% break it off. So with your bar graph, it started as an acid, and then it 100% splits up. Those are for strong acids. Comparatively, a weak acid, they want you to draw a two-way arrow. So when you place a weak acid in water, it's partially going to ionize. You're going to have a split from the hydrogen and whatever was the anion. But then you're going to see the reaction reverse itself, and it's going to go back to being an acid. So it only partially dissociates. How do you know which acids are going to completely break up in water and which are not? There is a rule that you have to memorize. So acids that are considered strong, There's 3 that we call binary, which is iodine, bromine, and chlorine. Hydroiodic, hydrobromic, hydrochlorine. Conveniently, they're all halogens in a row, kind of like the diatomics, I bring clay. Those 3 acids are strong, and any acid that has 2 or more oxygens compared to the hydrogens. So for example, H2SO4, if you compare hydrogens to oxygens, there's 4 oxygens, 2 hydrogens, there's double the amount, there's at least 2 more oxygens than hydrogens, that's a strong acid. First, if you looked at sulfurous acid, compare 2 and 3, there's only a difference of 1 oxygen. This would be classified as weak. So let me just give you a few more examples. What about HClO3? Okay, compare hydrogen to oxygen. The difference is 2, right? There's 1 and 3. So the difference is 2 oxygens. There's 2 more oxygens, so this is a strong acid. It would completely ionize, 100% ionize in water. What about carbonic acid? Would you label it strong or weak? Okay, if you said weak, you are correct. Carbonic acid is a weak acid. There's a 2 to 3, there's only 1 oxygen difference, and the rule says it has to have 2 more oxygens than hydrogens. What about hydrofluoric acid? If you said weak, you are correct. So notice there's not oxygens, that's this half of the rule, but the other rule is iodine, bromine, chlorine. Well, fluorine does not fit that category. Now, if I asked you about hydrochloric acid, this is considered a strong acid. This is something I would definitely star and highlight. It's easy to forget the strong acid rules. Okay, last thing about acids is a simple definition called polyprotic acids. We've talked about polyatomic before, poly meaning many. So this is an acid that has more than one, has many hydrogens it could dissociate. So HCl is not a polyatomic acid, but H2S, hydrosulfuric acid, is a polyatomic acid. It has more than one hydrogen that could break off. Okay, going to the other side of the spectrum, let's talk about bases. Bases have that bitter taste and a slippery feel. So a lot of household cleaners are basic products. I think soap or ammonia, Clorox are basic products. Like acidic things, bases also conduct electricity when in a solution. So a base can dissociate in water with charges that allow for a connection to happen with a light bulb and therefore conduct electricity. So remember, just like acids, we do want you to know the properties or characteristics of bases. In terms of indicators for a base, with our litmus paper, you're going to see litmus paper turn blue. And you're going to start seeing a lot of alliteration. Bases start with B, and you're going to notice bases have a bitter taste from our last slide. Bases turn litmus paper blue. In phenolphthalein, a basic solution, you drop a couple phenolphthalein drops in, it's going to turn pink. There are 2 types of bases, strong and weak, very similar to acidic in that strong bases 100% ionize or separate in water, and weak bases only partially dissociate. So for example, sodium hydroxide, when you place it in water, you're going to see 100% ionization. Ions are charged particles. You're going to see a complete breakup. How do you know which bases will completely break up? So who are your strong bases? This is a rule you have to memorize, and this is a very different rule than what are strong acids. So strong bases, you have to look at the periodic table, and any strong base is going to include a alkali metal or strontium or barium. And so if you notice, there forms like a little B on the periodic table. These are where your strong bases are. So lithium hydroxide is a strong base. Potassium hydroxide is a strong base because those are alkali metals. Strontium hydroxide is a strong base because it's in that little B. This is a little bit of a stretch, but if you, let me erase this. Strontium and barium Doesn't that almost say strong base? Like if you kind of fill in some letters. So barium hydroxide is a strong base. But if you were to go above strontium to like calcium hydroxide, well, that's in the blacked out area. That would be a weak base. It wouldn't completely ionize in water. Same thing for beryllium and magnesium or any metal over here. Okay, lastly, what happens when you combine an acid and a base is you actually form a salt. So I like underneath here, you have a base, potassium hydroxide, you have an acid, nitric acid, and it's really just a double replacement reaction. The two cations swap places, so K goes with NO3 and HOH, also known as water. So sometimes it kind of sounds scary of like, oh, what happens if you mix an acid and a base? Well, you end up, because acids and bases are on two different ends of the spectrum, they meet in the middle and they make a salt, as well as water. So we're going to kind of be bringing back Unit 10, using chemical reactions and balancing, but we're going to be only focusing on the reaction of an acid plus a base, called a neutralization reaction. We're neutralizing the acid and the base. Okay, this next part is we're going to be talking about theories of acids and bases, and there's two main theories that we're going to be holding you responsible for. So the first theory is called Arrhenius's theory, and he basically said that acids are compounds that when placed in water, they're going to dissociate and produce hydrogen ions. And bases are going to be compounds when placed in water are going to have hydroxide ions. So based on Arrhenius's theory, if I gave you a beaker that has lots and lots of hydrogen ions, it would be considered acidic. Or if I gave you a beaker that had a high number of hydroxide ions, it would be considered basic. So kind of what we just mentioned on the other side, if we put hydrochloric acid in water, which is a strong acid, we would see dissociation and there would be a lot of hydrogen ions. Same thing with sodium hydroxide. It would dissociate and split up, and we would see a high number of hydroxide ions, classifying this as a basic solution. So the only thing that didn't work for Arrhenius's theory is that ammonia, NH3, has properties of a base, and yet it doesn't fit the category of there's no hydroxides. And so this theory needed to be broadened, that Arrhenius's was pretty narrow. Bases have to end in OH, acids have to start with an H. And so a different guy, or two different scientists, brought in a broadening theory of what acids and bases and how they behave. So those two scientists were Bronsted and Lowry, and this was their theory. They said acids aren't just, they don't have to start with an H, but it's any compound that can donate a hydrogen in a reaction. And that bases would be defined as any substance that can accept a hydrogen in a reaction. So it's no longer kind of what it starts with and ends with, but can it donate a hydrogen or can it accept a hydrogen? You can also interchangeably say proton, and they're also just referring to hydrogen. I also have a bad acronym, and then Bronsted starts with a B. Here's a recap. Bases accept, acids donate. Because it can be easy to flip those. So here's a little mnemonic that can maybe help you. So Bronsted-Lowry had a bad acronym. Okay, so let's look at a chemical reaction and see if we can classify the acid and the base. So something I do is, here is HCl before the reaction, and then I look for its similar thing after the reaction. So here's our arrow for before and after. So HCl and Cl ion, and then H2O and H3O plus. And then I just look at what happened before and after. Well, before the reaction, hydrochloric acid had hydrogen, and then it's gone. So that means HCl must have donated in the reaction, and H2O absorbed it, and that's why it's now H3O plus. So based on Bronsted-Lowry's definition, acids are the one that donate the hydrogen. Well, hydrochloric acid donated it, so we're going to classify that as the Bronsted-Lowry acid, therefore making H2O the Bronsted-Lowry base. Notice we're classifying just the reactant side. We're going to handle the product side in a little bit. Okay, let's try another example. So first thing I do is, if the chemical reaction, I like to pair up like terms. So I see this ion before, and then after this reaction, I see that it has gained a hydrogen. So that indicates to me that H2O must have donated the hydrogen. And we know from our BAD acronym that bases accept and acids donate the hydrogen. So if water donated, that makes water the acid, and that makes this acetate ion the base. So if you guys noticed, water in our last two examples, one time it was an acid, one time it was a base. And so a substance that can act like an acid or a base is classified to be amphoteric. I kind of think of the word ambidextrous, like you can use both your hands. Amphoteric, you can act like an acid or a base. Okay, let's talk about now the product side. So we know on the reactant side, there's an acid and a base. And now we're going to talk about what's happening on the product side. So here it just says species that differ by the presence of one hydrogen ion. So a conjugate acid is going to be the particle that formed when the base gains the proton. So when the base accepts, and kind of the way you think about it is if the reaction reversed itself, it could like redonate that hydrogen back. A conjugate base is the particle that lost the hydrogen. So what is this? So this acid donates, it becomes a conjugate base on the product side. So once again, when an acid loses the proton, it then becomes a conjugate base because it could accept the hydrogen back if the reaction reversed itself. And then likewise, the base that accepts the hydrogen on the reaction side becomes the conjugate acid because it could then donate it once again if the reaction reversed itself. So now let's look at this chemical reaction and label everything, the acid and the base as well as its conjugates. So like we did before, I would still pair up like things, one on each side. And then I typically label the reactants first. So I look at NH3 and I track it. So before the reaction, it had 3 hydrogens. After, it has 4. That means it must have accepted during the reaction. So we know acids donate. That makes water the acid. And bases accept. So NH3 is the base. H2O is the acid. Well, we know that NH3, it becomes opposite. So if it was a base here and now it accepts it, now NH4 is the conjugate acid. And then H2O, if it was an acid on this side, it becomes opposite on the other. It's a conjugate base. Because if this reaction were to go backwards, it would just redonate. So this acting like an acid, this acting like a base. Another way to think about this is like your pair, the before and after, should always have one of each. So like you shouldn't have base and conjugate base. You should have an acid and a base. One of them has to be a conjugate because it's on the product side. So here you have a base and a conjugate acid. Here you have an acid and a conjugate base. And then a third way, I'm a little hesitant to share it because it's kind of a shortcut, but I want you to make sure you understand what's going on, is that in the pairing, the acid or conjugate acid, whatever the A is going to be, will always have more hydrogens than the other one. So this conjugate acid has more hydrogens here, and then H2O and OH, the acid always has more hydrogens in the pair. So let's do another practice problem identifying all 4 components. So the first thing is to match up like things. And so kind of the technical one is figure out who's donated. So HCO3, CO3, they've lost a hydrogen. So that's our donate. That's our acid. Therefore, H2O must be the base. Label that. And then we know in a pair, it's going to be the opposite on the other side. So if this was the acid, now this is the conjugate base. And if this was water was a base on this side of the reaction, arrow being the split, then it would be a conjugate acid. And just to confirm, the conjugate acid has more hydrogens than the base. This acid has more hydrogens than the base. And then lastly, kind of everything goes opposite when you cross over. So for example, hydrochloric acid is a strong acid that can donate, and it will become a base on the other side, and it will also become weak. So it was strong acid over here, weak base on the opposite side. So the stronger the acid or the base, the weaker its conjugate is going to be. Okay, we have 2 more problems left in the whole lesson. It says, write a balanced equation for the reaction that occurs with the cyanide ion and it accepts a proton from water. Okay, so we have a cyanide ion. It's going to react with water. They're saying that that ion is going to accept the hydrogen from the water, creating HCN. And then if water loses one, it's going to become a hydroxide ion. Okay, and then the question is the cyanide ion a Bronsted acid or base? So I'm going to match up like things. So if cyanide accepted, that would make it a base, and water would be a Bronsted-Lowry acid. So just to repeat it one more time, if this helps, there's Bronsted-Lowry had a bad acronym, bases accept, acids donate. And so because cyanide accepted, that classifies it as a base. Okay, last example, write a balanced equation for the reaction that occurs when phosphoric acid donates a proton to water. So I'm just going to try and draw this out. So it's going to get that. H2O is going to accept and form H3O plus. And then this one will be down one hydrogen, forming a negative charge. Is the dihydrogen phosphate ion a acid or a base? Okay, so dihydrogen phosphate ion, they're asking us what that is. So we know that the phosphoric acid donated the hydrogen, that accepted, and so this would be opposite, and if it's an acid on this side, it's a conjugate base on the opposite side. So the dihydrogen phosphate ion would be classified as a conjugate base. Okay, that concludes our lesson. I know that was a lot of information, and so please, please, please work on your practice so you know your properties, remember how to name things and your theories, keep them straight. Arrhenius versus Bronsted-Lowry. Thanks for listening. Hope you have a great day.